We're going to move on to the next speaker, Dr. Milagro Mottola from CONICET from Argentina. So you can put your presentation on, Milagro.
Let me see.
Okay.
Is sharing? Yes.
Yes.
Perfect. So, well, thank you very much to the organizers for the invitation. And well, today I'm going to share a small part of what I did during my PhD project at Instituto de Investigaciones Biológicas y Tecnológicas under the supervision of Dr. María Angélica Perillo. So, first of all, to give you a small framework, the topic of my PhD thesis was related to the biophysics of phospholipids. So why are the phospholipids so interesting? This is mainly because they have several physicochemical properties that make them unique. Among them, we can highlight their amphiphilic nature, which allow them to be surfactant agents. So this means that they can modify the surface tension at the interface between two phases. So as a consequence, if we spread the phospholipids onto a water phase, or if we disperse them into a water phase, they can form different supramolecular structures with specific characteristics that are geometrically constrained. So in this sense, different industries, such as food and pharmacy industries, have taken advantage of the phospholipid properties to use them as encapsulation carriers. So, which can, according to the chemical nature of the molecule we want to encapsulate, is which platform we are going to use. So, among them, the most known platforms are the liposomes, uni or multi-lamellar vesicles, and also the emulsions, which were of interest of my PhD project. So, briefly, we should know what emulsion particles are. So basically, an emulsion is a two-phase system that consists on finally dispersed stable droplets. This is called internal phase or dispersed phase, in a second continuous phase in which it is immiscible. So these colloidal systems can be stable for a certain amount of time thanks to the presence of an emulsifying agent, such as the phospholipids. So we have direct emulsions, which are oil and water, as these examples, as well as inverse emulsions, which are water in oil. So both types of emulsions can be prepared through different methods, which normally involved an external physical force, such as stirring or ultrasonication. Well, after checking in the literature, we can find that there are still current challenges in the emulsion formulation. Among them, we can highlight the absence of preparative techniques that provide quantitative data for a rational and facilitated formulation, and the little understanding of the mechanisms that govern the stability of oil, water, and water in oil emulsions. So this leads us to think that the study of surfactant molecules in a liquid-liquid interface is really important. But we faced the problem that there are still few reports of the liquid interface about studies of the liquid-liquid interface. So this motivates us to think that we still need good experimental models for studying this kind of interfaces. So, having this in mind, my thesis project aimed to study different oil and phospholipid mixtures and to evaluate their capacity to form emulsion nanoparticles. So to achieve this general objective, we have planned several specific objectives, but the most important was to find a useful technique that allow us to study a liquid-liquid interface, but with a high control over the different parameters. So in this sense, since a particle emulsions owns its stability to how stable is the monolayer of the surfactant between these two phases, we decided to use as experimental model Langmuir monolayers between two liquids. So in order to use this model, the first challenge to overcome was to design and build the Langmuir trough, since at that moment there wasn't such equipment available in Argentina. So here in the left, we can see some pictures of the equipment that we built for our lab, and we can see in the right some schemes that shows their main characteristics and dimensions. So this homemade trough has an internal step to seat the barrier, to seat the two barriers, and mark the height of the lower face. And the barriers have transversally different tunnels or holes to allow that the upper face to flow freely. So for our experimental system, we select two phospholipid models, HPC and DPPC, an aqueous phase, which was water, and an upper phase, the hydrophobic phase, which was mineral oil of acetylene. So this mineral oil normally has different compositions according to the fabricants. So we characterize our own mineral oil, and it was composed of saturated alkanes with different chain lengths. So regarding the Langmuir film technique, it's important to know that is normally used to study monomolecular layers of phospholipids, but at the air-water interface. So here we can see a scheme of the traditional configuration of this kind of equipment. And in this situation, normally we spread at the interface a chloroformed solution, and sense with the aid of this Wilhelmy plate, the change of the surface pressure according to the compression of the monolayer. So from these experiments, we can obtain rheological and thermodynamic parameters, such as the mean molecular area, the compressibility of the monolayer, as well as the free energy involved during the compression process. So the basis here, the basis of the Langmuir monolayer at the oil-water interface is similar, but it's noteworthy that at the oil-water interface, the Wilhelmy plate is usually immersed in water and in the oil phase and in the water phase. And other difference is that the surface tension of the clean interface in the case of air-water systems normally should be 72 if the subphase is water, and in the case of the oil-water interface, we can talk about an interfacial tension, which in this case of mineral oil and water is 37. So first, using the model phospholipid, which was phosphatidylcholine, egg-phosphatidylcholine, we test and compare different techniques for the lipid field preparation. So the adsorbed monolayers were formed by either putting by either pouring the phospholipid dissolution onto the oil-air interface, or in the previous oil-water or in the previous formed oil-water interface. This kind of preparation methods lead us to obtain adsorbed monolayers, but on the contrary, we have a third method in which we form spread monolayers, and we spread first the solution over the air-water interface, and then we carefully add the oil phase. So after different experiments, which I'm not showing today, we conclude that the last method, this one, has a good reproducibility, and it was easiest to perform. So in another study here, we use DPPC as a model phospholipid in order to compare the thermal behavior at the air-water interface and at the oil-water interface. So as we can see in this plot, we have the isotherms performed at the air-water interface, and below in this one, the isotherms obtained at the oil-water interface, in both cases at 3 different temperatures. So if we see the isotherm at 25 degrees, we can observe a phase transition between a liquid expanded state and a liquid condensed state. At a lower temperature, we can observe only a liquid condensed state, and a higher temperature, we can see that the phase transition occurs a higher surface pressure because the liquid expanded state is stabilized.
5 minutes, Milagro.
Okay, so similar behavior can be observed in the oil-water system here, but we can see that the phase transition occurs at a higher surface pressure. Yes, so this is mainly because the alkane molecules of the upper phase are intercalated between the hydrocarbon change of the phospholipids. Also, the compressibility values were smaller for the DPPC film at the oil-water interface than those calculated for the air-water interface. And besides, we found that all the DPPC films studied at different temperatures requires different amounts of energy to be compressed, up to 20 millinewtons per meter. So as a general trend, the free energy of compression values were always higher for the oil-water interface than those obtained for the air-water interface. So finally, another kind of experiments were made in order to connect the data from the films at the oil-water interface with emulsion formulation. So for this purpose, we made absorption isotherms, where the interfacial pressure is modified by the addition of different amounts of molecules. So as we see in the graph, we measure the interfacial pressure in function of time after several unconsecutive aggregates or additions of molecules. So from this experimental data, we can obtain the equilibrium pressure of saturation, and having this into mind, taking this into account, we can correlate the information from the isotherms obtained directly with the Langmuir trough, and we can interpolate this pressure and obtain the mean molecular area of phospholipid. So with this information, and assuming we want to form a spherical emulsion particle of a certain diameter, we can calculate with the aid of different geometrical parameters, for example, the number of lipids molecules that we're going to need to cover this complete nanoparticle, the volume of oil phase that we are going to need to use in order to have a stable emulsion, and theoretically predict the oil surfactant molar ratio that we are going to need in the case that we want to have stable droplets of different sizes. So just to summarize, we have some general conclusions. First of all, we could successfully apply the Langmuir technique at the liquid-liquid interface and select which was the best method to prepare them. And in comparison, if we see the monolayers formed at the air-water interface in contrast with the monolayers at the oil-water interface, they are always more expanded. They have a higher transition energy and surface pressure transition. And we found that, well, the alkane molecules of the upper phase are always intercalated here between the hydrocarbon change of the phospholipids. And for the last part, all the results that we obtained in the emulsion system are like a first approximation of how we can use this Langmuir field model in the liquid-liquid interface to obtain preliminary information to lead the formulation of stable emulsions. So that's all. Thanks for your attention. And I want to acknowledge to all the institutions that give us financial support and all the lab members of IIBYT.
Okay, thank you, Milagro. Questions? I cannot find any question here. I have one. I would like to know, I know this is a model. You are trying to use monolayers as a model for emulsions, but would this be worth for nano and micro emulsions, or just for nano emulsions? I was thinking about the arrangement of the monolayer, and because you can have both kinds, yeah, nano and micro emulsions. What do you think about?
We test actually just with nano emulsions.
I see.
To obtain particles between 100 to 400 nanometers. I'm not sure if it will be useful for obtaining the small, the micro emulsions, but there's still a lot of parameters to play with. In my case, I use these parameters from the Langmuir monolayers and only make changes in the molar ratio of the oil and the surfactant, but there's also important the concentration of the lipid in the aqueous phase, and also the amount of water system. So there's still several experiments to be made.
Okay, congratulations.